Okay, let us discuss one fact. Let me. The fact is that you can put all the complex points or the R2 points into a sphere. Okay, so this is a very interesting fact that you can take the infinite plane and put it onto your hands just on a sphere. But how can we do that? Let us discuss that fact. So, for proving this fact, we'll prove this by doing some analysis. We'll construct a function which will be bijective in between the sphere and the complex plane. Okay, so you can see here, I just taken sphere S and the complex plane xy. This xy plane is complex plane, and I took a sphere S and put that sphere above the origin. Okay, and the feature of this sphere is that its center is at 0, 0, 1 and its radius is 1. Okay, we take that sphere and put the 0, 0, 1 point as its center and radius 1 so that it would touch the origin point 0, 0, 0. Why we will doing this? So this will be clear after viewing this proof. Okay. Now we want a map F in between the complex plane and the sphere S. Now take any arbitrary point x, y, z. Here in this figure, you can see that x, y, 0. This is a point of complex plane. Actually, we are taking complex plane on 3D surface. So the third coordinate will be 0, and the function is constructed in such a way that this point A will go on a point B on the sphere S in such a way that when we join this point A and this vertex point O dash by a line, it will cut on a point on the surface of S and call this point B. So we just send this A on that point. Okay. So you can see that if you take any point on the complex plane of this circle on which A lies, okay, circle, corresponding to each point on the circle, you will find a circle above on the surface S, on the surface of a sphere S, so that each point of this circle by each point of the circle will go to exactly one point on that circle of the sphere. So if we are giving any arbitrary point x, y, z, how and what will be the point on the sphere, what will be the coordinate of the point sphere, we will derive that point. This is the motto of this lecture. So you can see that as we make an analogous, that the point will be on the intersection of the sphere and the line joining the vertex O and the point A. So as we all know the equation of line, if A and B are two vertex points, then equation of line of the line segment AB is given by lambda A plus 1 minus lambda B. So this x, y, z which is on that line can be, this x, y, z can be represented as lambda times 0, 0, 2 plus 1 minus lambda x, y, 0. Here 0, 0, 2 is the vertex point. This point is 0, 0, 2 and this point is x, y, 0. And this point B which lie on the sphere which corresponds to this point A is also lie on this line. Hence B, that is x, y, z can be represented as lambda times 0, 0, 2 plus 1 minus lambda times x, y, 0 for some lambda from this open interval 0 to 1. We are not taking close interval 0 to 1. Why? When we take 0, we put 0 lambda equal to 0 here. So x, y, z will be x, y, 0, which is not the case. Okay, these both points cannot be same until and unless x, y, z is 0. This point and this point can never be equal. It only can take same value at the origin by the construction you can see this. So you cannot take lambda equal to 0 at all time and lambda is equal to 1. When you take lambda is equal to 1, you will get xyz equals to 0, 0, 2. But when you join the points, the vertex point and the point A, and you move this line and you move this line towards infinity, then at some point this point goes near O's, but it cannot reach the vertex at any finite point of the complex plane. So we cannot take lambda is equal to 1 here, but we can take lambda is equal to 0. That lambda equal to 0 will indicate the point origin, only point at origin. Okay. Now this is all the analysis part, the calculation. You can see that x, y, z that is equal to 1 lambda times 0, 0, 2 plus 1 minus lambda times x, y, z. When you expand this, you will get this expression. And also, this x, y, z presents on the sphere as whose center is at 0, 0, 1 with radius 1. So, it will satisfy the equation x square plus y square plus z minus 1 square equal to 1. When you solve this equation for lambda, then you will get an quadratic polynomial in lambda and whose discriminant will be 16. After solving some calculus part, you will get this, and by applying the quadratic formula you will get lambda is equal to either 1 or x square plus y square by x square plus y square plus 4. But as we earlier see that lambda cannot be equal to 1 because this lambda corresponds to point at infinity, but we are taking x, y, 0 as a finite one on the complex plane. Okay, so this lambda will be equal to this value x square plus y square plus 4. Now we will get the value of capital XYZ, the point on the surface of the sphere corresponding to the point XY0, which will be equal to 1 minus lambda times x plus 1 minus lambda times y, 2y, and substitute the value of this lambda here, we will get this expression. And that means what? And that means we send this point xy0 to this point on the sphere, where xy z, not z, this is xy0. xy0 is not the point at infinity. When xy0 is infinity, then we take the value as vertex value, that is 0, 0, 2. So this is a bijection. You can see that this whole complex plane, we take in a sphere on the complex plane and send any arbitrary point xy0 to a point capital XYZ, and whose value is equal to this, and this function is a bijective function. And it is bijective means for each point on complex plane we get an unique point on the sphere, and each point of a sphere represent a unique point of complex plane. So this is the proof of this fact. Okay.